Well, it's so good to see everyone, and for those of you who have come before, you came back. Thank you. That's so nice to hear. So, when we look at Michelangelo's work, we think to ourselves, Michelangelo created this beautiful sculpture. He invented this sculpture. Out of his mind, he created something. But Michelangelo writes, no, that's not what happened. I didn't invent it. I didn't make it. The sculpture is already complete within the marble block before I start my work. It is already there. I just have to chisel away the superfluous material. And here, this is a beautiful sculpture because you can see him chipping away at the sculpture. But then you take the most famous sculpture, perhaps in the world, the David, and again he said, I saw the angel in the marble and carved until I set him free. He didn't invent this. He said it was there. He discovered it. And what's the difference between invention and discovery? Where do our literature ideas come from? It was the best of times, it was the worst of times. There is enough in the world for everyone's need. There is not enough for everyone's greed in the Upanishads. Was this invented or discovered? Where do our paintings come from? Is somebody inventing them or are they discovering? And I think we say, we invented all this. People invented this. Dance. Where do our dance ideas come from? People invent them, or do they discover them? Where do our sports ideas come from? So I have this slide for Giri here, because he's an avid cricket fan. All I know from cricket is that this person plays somewhere in Bangalore. But that's it. But let's get more to the math and science now. Where do our ideas in math come from? So in math, when you're a small child, first grade, second grade, excuse me, you do subtraction problems. The teacher gives you 12 minus 3, 9 minus 4, 17 minus 9. And then one child says, why does the big number always come first? Can't we do 3 minus 15? The teacher says, no. The big number always comes first. And in fact, in the world, the big number always did come first until somebody invented negative numbers and doubled the number of numbers we had instantly. And then you get to third or fourth year, fifth year, and then we learned square roots, the square root of 9, the square root of 16, and some students said, can we take the square root of minus 25? And I said, no, you can't do that. Only square roots of positive numbers. And then somebody invented imaginary numbers. Said, no, square root of minus 25, that's okay, 5i. Even now, we have people here who, if I ask them about dimensions, they'll say, oh yeah, I know what 1, 2, and 3 dimensions are. You have a line, you have a tabletop, you have the 1, 2, or 3 dimensions. And I wonder, well, what about 1.46 dimensions? No. Dimensions only come in whole numbers. But in fact, Mandelbrot and other people invented fractals in the 20th century, and this has a dimension of 1.46. We invent different ways of looking at this, and this is mathematics. And now we have the electron, and we all go to school and we learn the electron has a negative charge. The electron is part of the atom. The electron travels around the nucleus. All of these facts about the electron as if it's real and we discovered it, and not that we made it all up and invented it. Our school books are very good at explaining what we know, what's left over after the science is done. They are not so good at explaining how we know. So let's do a little experiment. On your armrests, there are 2 pieces of cellophane tape. And if you lift the top one, if you separate the 2, and you lift the top one and the bottom one, you'll see that there's this remarkable force of attraction between them. And in fact, if you go to your neighbor and you take your top one and your neighbor's top one, then we find out that they repel. That there's an invisible force causing them to attract or causing them to repel. So this is the beginning of our understanding of charge. And we say, how can we explain the attraction? How can we explain the repulsion? So we do the experiment, and we see this, and we have to explain it. So we say, oh, I know. There are two kinds of charge. We'll call them top and bottom, because the top piece of tape had one, and the bottom piece of tape had the other. So we'll call them T and B. Well, if you go around the world and talk about T and B, they won't know what you're talking about. So let's use what everybody else says. One is plus, one is minus. And so plus, top it repels top, and bottom repels bottom, and top attracts bottom, or plus and plus attracts, like charges attract. Ben Franklin said, you know, you don't need two kinds of charges. We can explain it with one type of charge. He said, how? No, we have the top and the bottom. Why one? He said, no. The top, the tape starts off neutral. The top gets 4 extra things, and the bottom one loses 4 things, and that's how you get the 2 charges. There's only one thing moving. And so Franklin makes this jump at our understanding. So we now know there are these charges that do these nice things. And so we start asking questions about these extra things, these charges. How big are they? Where do they reside? Can we isolate them? How do they behave? Are they in all matter? Can we use them for our own purposes? And again, Ben Franklin, who did a lot of studies on this, he said, oh, you know, when you walk on the carpet and then touch the doorknob, you get a shock. That's the same shock as when the lightning hits. It's just a lot bigger, the lightning. But he said it's the same. It's like, really? Those are the same? And again, we begin to understand. If you take these static charges, you can have a machine that makes these charges instead of just ripping off pieces of tape. And when you do that, all of the hairs get the one type of charge, and you can see how they separate. Just like we had the repulsion of the tape, you now have the repulsion of all the hair. So it looks good and it's fun to do at a science museum. And then we realize that, oh no, the number of charges are conserved. If we start off before touching them with a -10 and a 0, we get -5 and -5. If we get -10 and a charge of +4, then it's -3 and -3. +2 and +6, +4 and +4. It just, you don't lose any, you don't gain any. And just, you know, so it's like this. If you start off with 4 and 0, and you touch them, you get 2 and 2. That's a good trick to know. 4 and just like that for the children. When we try to discover this, charge is conserved. This is an amazing thing. In physics today, we only have found 7 things in the entire world which are conserved. Charge is one of them. If you're able, as a school student, to find another one, you win the Nobel Prize. That's how incredible it is, to find something which always stays the same. Then Coulomb does this experiment way back when, and he says, you know what, I want to measure how strong the force is. When these 2 pieces of tape attract or repel one another, I want to measure it. And so he does a very careful experiment, and he measures it, and he puts an equation down, and now we think we understand about these charges. We understand it so well, in fact, that we can make batteries, which were made in 1790, but certainly we're more familiar with the batteries on the top, and we have cars now which are run by batteries. And then, at a different time in 1820, Ørsted, a teacher, was doing an experiment. And he said, look at the compasses in the top picture. All the compasses point north, as we expect. We use it for navigation. But when he put a current, when he got those charges moving in a wire, he noticed that all the compasses shift. They don't point toward the wire or away from the wire. They point in a circle around the wire. And Ørsted said, you know, electricity and magnetism are somehow related. But of course, the big question is, how does the compass know that the current is there? How is it that how does one charge know that the other one is there? How does this know where to attract? How does it know to go this way? That's a huge question in science, and it's a question that Newton asked with, if I drop my pen, how does the pen know where the earth is? We just say, oh, gravity. Well, that's just a word. How does the earth know where the sun is? And Newton, a great mind, said, I don't answer those questions. That one's too hard for me. But Michael Faraday, who was a poor student, a poor boy, actually he had to leave school at 11 years old. He had a speech impediment and he wasn't liked in school. And he left school at 11 years old. He didn't know much. He hadn't learned much. But thankfully, somebody running a bookbinding store gave him a job. And he got to work in the bookbinding store and learned how to sew books and do all this. And then he started reading some of the books. And some of the books were about science. And so he asked the person who ran the store, there's a little corner of a shop here, a little corner we don't use. Can I do science experiments there? And he said, sure, you can do that. And Faraday starts doing experiments. And he starts trying to explain the experiments. And Faraday, to cut to the chase, becomes arguably the best experimental scientist of the 19th century. He's the best. And he discovers, there's this question of, if you can make magnetism from electricity, if electricity can affect the magnets, can we do something to the magnets to make electricity? That would be nice to make electricity. Faraday's the one who figures out how to do this. But he doesn't know any math. He only went to school to 11 years old. He doesn't know any math. And so there were physicists who said, no, Faraday, you're not really a physicist because you don't know math. He said, but I discovered electricity. No, not good enough for us. You have to know the math like us. What we have to take from the story about Faraday is he was a poor boy who didn't know math. If he came to most of our classes or schools and said, can I study physics with you? We would say, how much math do you know? You don't know math? No, you can't study physics here. We don't allow you to study physics unless you know more math. If he's working in a store with an education of a fourth grader, and he says to the person who owns the store, can I do some science experiments? They're never saying yes. And so there are children all over India. There are some children who may be Michael Faradays, and we're not giving them the chance to show what they can do because we're saying, you're not doing it the way we want you to. But because Faraday doesn't know the mathematics, he draws these pictures. He says, when one attracts the other, I think it sends something out in the space. The space becomes distorted somehow. It's as if there were lines in the space. And they say, lines? Yeah, if I have the lines, I can explain everything I observe. You like this model of lines. And he draws the lines for magnets, and he draws the lines for positive charges, and he explains how he creates electricity. And then along comes James Clerk Maxwell. Maxwell knows mathematics. And he says, let me look at those Faraday lines and put them into a mathematical language. And when he does, when Maxwell takes Faraday's ideas and adds another idea of symmetry, what he realizes is that the electric field will create the magnetic field, which will create the electric field, and then creates the magnetic field, just as Faraday thought it would. But what Maxwell realizes is that when the electric field creates the magnetic field, those lines, it doesn't do it here, it does it here. And when this one creates the magnetic field, it does it here, and here, and here, and here, and here, and here, and it marches across the room. And Maxwell said, I can find the speed that these field lines move. And when he does that, it turns out to be the speed of light. And so Maxwell says, I think light is part of this electromagnetic wave and these field lines that Faraday did. And now, not only are the field lines believed to be real, that Faraday invented, but we think everything is fields. We think the fields are more real than the mass. So we have those fields. And then along comes, in the 1897, some of you remember there used to be televisions that weren't this thick, but they were much thicker. And if you turned them off, there would sometimes be a white dot in the middle. Those had tubes in them which could shoot things to the front of the tubes. And it was very nice because we could shoot this thing to the front. We could also have it by using magnets, or we could have it go from the top all the way across, then the next line all the way across, the next line all the way across, the next line, and then we'd say, oh no, instead of just lighting up everything, let's turn them on, off, on, off, 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 and we'd make a whole picture. The picture could change, we had television. Well, that tube, it existed, but nobody knew what was hitting the front, and then J.J. Thomson realized that in fact it was something he would call the electron. So this is actually J.J. Thomson's voice telling you about what he discovered.
Could anything at first sight seem more impractical than a body which is so small that its mass is an insignificant fraction of the mass of an atom of hydrogen, which itself is so small that a crowd of these atoms, equal in number to the population of the whole world, would be too small to have been detected by any means then known to science.
Thomson discovered or invented the electron. What's good also to remember about Thomson is in the laboratory where he made this discovery, he wasn't allowed to touch the equipment because he was so awkward. Other words, tell us what you want us to do, we'll do it for you. So once we have the electron, we then can explain things like the photoelectric effect, where light can free electrons from substances, or that light can behave like a particle when it does that. In this case, light can hit, that's interesting. Okay, I don't know why that's happening. Anyway, so light can have a collision with this. There it is. Light can have a collision, so the light comes down, it hits the electron moves one way, the light moves another way. And then the question was, well, how big are these charges on these electrons that Thomson discovered or invented? And Millikan does this oil drop experiment, and what he finds is that if he takes an oil drop from a little tiny oil drop, and he can make it go up and make it go down, he can make measurements. Now, it doesn't look very hard. He's doing this through a microscope. And he's trying to keep the same oil drop going for 3 hours, 7 hours, 3 days. And he just did this. I mean, I remember my students saying, did he get paid a lot of money for that? I don't know how much money he got paid for doing this, but there was some reason he wanted to do this. And he discovered that these charges, you can have 5 or 11 or 20 or 30, but you can't have 3.5. You can't have 2 1/3. That somehow the charges are one at a time. Similarly, at the same time, we have Ernest Rutherford discovering the nucleus. Now, how did he discover the nucleus? Like this. So, some of you have this piece of paper in front of you. What I'd like you to do is take the piece of paper and have somebody next to you, without looking, see the person on the right not looking, and just take your pen and hit the piece of paper, have the person move the piece of paper, do this 10 times and see how many go in the circles and how many don't. So just do this, don't look, and the person will keep moving the paper, and see how many go in the circles and how many don't go in the circles. I've not usually done this in this kind of laboratory environment, but So I need you to count how many went in the circles and how many did not go in the circles. Out of 10, how many hit a circle? So with a show of hands, out of 10, how many people had 1 hit a circle? 2 hit a circle. 3 hit a circle. 4 hit a circle. 5 hit a circle. 6 hit a circle. 7? 8? Nobody wants to go to the casino? 9? 10? Okay. So, if I add it all up, I'd say about 5 was the biggest, 4 or 5. If you hit the circle 5 times out of 10, that must mean that half the area is circles. I know the total area of your card, it's written on the bottom, is 50 square centimeters. So that would mean the coins would be half of that, 25 square centimeters. And there's 1, 2, 3, 4, 5, 6, 7, 8. So that would mean there's each card, each circle is 3.1 square centimeters. And so if I take that, I know the size of the coin, and therefore I know the size of the circle. I can measure and I can use an equation to get the radius of the circle. So without knowing any one circle, by just dropping the pen, we were able to calculate, and you can measure this, you can take this home, measure it, it's about 1 centimeter, it works. So let me show you what happens. If you could take a moment, and you go on the back of this, draw a square, a little square, very quickly, just, don't take out your scales and protractors, just 1, 2, 3, 4. And let's say not 8 coins, not 8 circles in there. Let's say there's 1 shape in there, just a single shape. And half of the drops hit the shape. What might the shape look like? Just draw in there what you think the shape might look like. And I'll show you what I mean. Some people will say, it looks like that, because half of them would hit the red, half would hit the white. And somebody else says, no, I think it would look like this. That's also a good answer. Half would hit. We don't know what the answer is, but if half hit, we know that's an answer. Or somebody may say, ooh, that's clever. Half hit, half don't hit. So we'll do that again, but this time, we'll do this now, but what would it look like if you drew a square, and I told you only 10 out of every 100 hit? I did it 100 times and only 10 hit. What might the shape look like? And I think you would agree it looks something like this, or it looks something like this, about 1/10 of the area. So we do it again. And we say, what would it look like if it was 1 out of 100 it hit? And I say, oh, it would be small. It would be something like this. And then at the end I say, okay, let's do it one more time. 1 out of 10,000 hit. And you say, oh, if I draw a dot, that's too big. 1 out of 10,000 hits. Rutherford did an experiment very similar to this. He didn't drop his pen, he dropped these things called alpha particles. And when he dropped them onto a very thin piece of gold, he used gold because you can hammer it so it gets very thin. He didn't use gold because he has a lot of money, so I'll use gold. He didn't have a big research budget, we better use gold. No, he used a very thin, and he dropped these alpha particles. And what he found was that they all went through. They all missed. How many missed? 1 out of every 100,000 hit. 1 out of every 100,000 hit, and all the others went right through. And so 99.999% go through. So Rutherford said, matter is mostly empty space. It appears solid, but it's mostly empty space. And he says, the little tiny parts of mass where 1 out of 100,000 times you hit it, I'll call that the nucleus, the center of the atom. Now, just for those of you who worry about the correct physics and say, he didn't drop out. No. The conclusions are right. He didn't drop the alpha particles, he shot them horizontally. And it wasn't just hit or miss. Sometimes they traveled in paths, hyperbolic paths, and from that he could determine the nuclei. But the conclusions are right. So Rutherford discovers the nucleus. Let's hear from Rutherford. This is a tape of Ernest Rutherford.
The bother is that a nucleus, as you know, is a very small thing, and we know very little about it. I had the opinion for a long time, that's a personal conviction, that if we knew more about the nucleus, we'd find it was a much simpler thing than we supposed. That these fundamental things, I think, have got to be fairly simple. But it's the non-fundamental things that are very complex, usually. I am always a believer in simplicity, being a simple person myself.
So Rutherford says there's a nucleus. Thomson tells you there are electrons. And Niels Bohr says, I think I know how the atom looks now. The nucleus is the center, and the electrons circle around it. And with this picture of the energy levels of Bohr is able to explain the 4 lines that we see from hydrogen. Hydrogen gives off colors, and he gets the colors completely correct. And that's quite an accomplishment. But he does more than that. He also predicts that if the electrons jump from one orbit to another orbit, you could also see very high energy lines, but we can't see those. Our eyes don't detect those. That's okay. Somebody built an ultraviolet detector so you could see them, and Bohr got all the numbers. He predicted the exact numbers. Then he said there's another set of colors, but our eyes can't see them because they're in the infrared. But somebody invents an infrared detector, and once again, Bohr predicted what the colors would be, and everybody said, he's on to something. But of course, new questions arise. What do you mean the electron's in a circle? How does the electron get from one circle to another circle and never be in between? And so it puzzles us. Why are they in the circles Bohr says? He made up some rule, MVR equals NH bar, but why? And then along comes de Broglie. De Broglie's a student working on his PhD, and he has this idea. He says, you know how light used to be a wave? Now light's a particle. Sometimes it's a wave, sometimes it's a particle. Well, the electron we know is a particle. Maybe it's also a wave. And I said, what do you mean a wave? He said, you know, like a wave. And so this is for his PhD thesis, and the question is, do you give him his PhD? And everybody's looking at this saying, I don't understand this. Do we give him his PhD? They finally go to Einstein, who says, he knows enough physics, give him his PhD. But de Broglie says if these are electrons or waves, then on a string they would look like the top pictures, but they would be, to fit like as waves, they would have to be in certain circular orbits and not others. And that's why they're in certain orbits. So he has these things, and then that seems to make sense until Schrödinger comes along and says, I have a better idea. Instead of worrying about the wavelength of the electron, I've invented something in mathematics called the wave function, and I give it this Greek letter psi. And that's the electron. They say, what is the wave function? He said, no, it's just math. He said, no, but you're telling me the electron's math? Yeah, the electron is just math. It's just this psi. It's just this wave function. I say, and can we see the wave function? No, you can't see the wave function. Does it have properties? No, it has no properties. Oh, it has to fit an equation. They say, well, how do we know if it makes sense? If you take the wave function, you can find out how it fits into a box. If you square the wave function, it tells you the probability of finding the electron in certain locations. So if you look at the bottom right diagram, it says that the electron in a box, the electron will go back and forth, back and forth, back and forth. And the probability that it will be in the middle is very high. So sure, that makes sense to me. An electron goes back and forth. If you keep taking pictures of it, if you somehow could, keep taking pictures of it, most of the time you'll find in the middle, a little less here, and at the walls it'd be very rare. So that makes sense. But then Schrödinger says if the electron has more energy, then it's the middle picture on the right. And now the electron's going back and forth, and half the time it's on the left side, and half the time it's on the right side. But you'll notice in the middle, it's never there. The electron will never be in the middle. And we say, wait, the electron gets from the left side to the right side, but is never in the middle. Yes, that's right. But this is not how I imagine It's like, no, this is what we think electrons do. And then we put in the textbooks all these pretty pictures, and we say, that's the probability of the electron in the hydrogen atom. We say, oh, okay, now I understand it. But we don't understand it. So then we do this model. Thomas Young had done this experiment where he sent light through two slits, and he saw that the light would hit in certain locations, the white locations, and wouldn't hit in the black locations. And he said, see, so light plus light can make dark, and that's how we know light is a wave. Davison and Germer in New Jersey are doing an experiment, and they're shining electrons at a metal. And they're looking to see what happens when the electrons go through the metal. And they look and they say, oh, look at this, it goes here and there. And they're doing their experiments. And then they come to Davison is taking vacation in England. And he goes to England, and he's sitting in the back of this talk, a physics talk. And the person says, oh, and we have this new theory by de Broglie that electrons are waves. And we have the first evidence of electrons are waves from this group Davison and Germer in New Jersey. And Davison says, me? Really? I didn't know. I didn't know what these results meant. And Davison and Germer said, wait, we have better results. And all of a sudden, we start doing the experiment. We send electrons through slits. And as you saw, they keep landing in places, but they never land in other places. The electron lands in some places and not in others. So millions of electrons go through, and they land in some places and not in others. To better understand that, I want to do a quick experiment here. So this, I didn't put coins. I hope people might have, I know this is, you all have 500 rupee notes, but if you have a coin, so we take the coin, and we just draw this and that, 1, 1, 1, 1, 1, 1, 1. I'll explain it. So you start at the top one. I flip the coin. If it turns out it's heads, I go to the left one. If it turns out it's tails, I go to the right. Then I flip it again. And I go to the left, or I go to the right of the left one, or I go to the left or the right of the right one. And I do that over and over again, and then I look to see where do they land. And if we had the time and everybody had enough money to do the experiment, then, or I had enough money to put them at each chair, then what would happen is, if I asked you, where did yours land? I said, who's landed at A? A few people would raise their hand. The lucky people, the people who got heads, 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 heads. The people who got tails, 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 tails would say it landed at E. But most people would say it landed at C. There's a probability most of them will land at C. And that's somehow what the electron does. The electron goes through a slit, and sometimes it goes left, sometimes it goes right, and we have no idea which way it will go. But we know, if we do it with enough of them, how many will land at each position. And we can try to better understand where they're going and how they're going, and there are ways to do that. To make the slits smaller, we can try to understand where they are, but then if you do that, the direction they go is not known, so it becomes more complicated. This is the first conundrum. What causes the electron to travel as it does? If you take two identical electrons and two identical sets of conditions, you get different outcomes. Why won't those electrons behave properly? Why does it, the electrons certainly don't have rupee coins that they're flipping. So what determines where they will go? The second conundrum is if the electron has two slits to go through, it lands in certain places, not in others. And this is the conundrum which people still struggle with today. So when electrons go through two slits, they land in a place. Let me explain to you in a simple way. We take one electron at a time, one electron, and we shine it. There are two slits, A and B. but we're going to close slit B. So if the electron gets to the screen in red, it must go through slit A. And when we do that, it doesn't go straight, there's a probability, but it lands somewhere in the green, always. Always lands in the green. Then we do it again. This time, we'll close off slit A so we know it goes through slit B. And when we do that, now it lands in the yellow. And that makes sense. They all land there. And one was in front of the A, one was in front of the B. That's good. But if we open both slits, then they land in the middle. So let me explain it a different way. If they go through slit A, they land in the green. If we know they go through slit B, they land in the red, in the orange. If we don't know which slit they go through, if we give them an option of going through two slits, then they land in the blue. One more time. If slit A only is open, and the electron only sees slit A, it goes to the top. If only slit B is open, it goes to the bottom. If slit A and slit B are open, it never goes to the top or bottom. It always goes to the middle. And so you have to wonder, how does the electron know two slits are open? How does the electron... So if you only have one slit open, it behaves one way. As soon as you open another slit and say, you have a choice, the electron will never land where it used to land. It will only land in these new places. Now, what we don't know, it behaves one way. When we do know, when we know, it behaves one way. When we don't know, it behaves another way. Our role is determining how the electron behaves. It's not true for a falling ball. You don't have to look to see the ball. It's going to fall. The water will boil. Now, there are people who said, I'm going to trick those electrons. And people are still trying to trick those electrons. Here's the way they try to trick it. I'm going to let the electron see two slits, A and B. They're both going to be there. The electron can go through slit A or slit B. If it goes through slit A, I'm going to detect it, so I'll know it went through slit A. If I don't detect it, it must have gone through slit B. When you do this experiment, they all land where the orange is. If you take the detector away from A, after the slits, take the detector away from A, now they all land in the blue. And this is a very simple trick. Physicists for the last 50 years have been working on more and more sophisticated tricks to try to understand what the electron is doing. Niels Bohr said, if this makes sense to you, then you don't understand it at all. Or another way he said it, those who are not shocked when they first come across quantum theory cannot possibly have understood it. So if you say, that's fine with me, Bohr is saying you don't understand it. So then Paul Dirac comes along and he says, oh, I have a model for the electron. If you do this, then there'll be another, something like the electron, but have a positive charge. And Anderson finds that and does that. Let me give you another example of these wonderful electrons we discovered or invented. Electron tunneling. So normally, if you think of this as a wall and the red as a cricket ball, if I throw the cricket ball to the wall, it's going to bounce back. It's not high enough to go over the wall. It's just going to bounce back. And that's what we would expect from an electron. We hit it against the wall, it doesn't have enough energy, can't get over, it'll bounce back. That's not what happens. Most of the time it bounces back. But every once in a while, it doesn't bounce back, it somehow ends on the other side of the wall. It's like, wait, how did it get through the wall? We don't know. Did it go over the wall? No, it didn't go over the wall. We know it didn't go over the wall. It doesn't have enough energy to go over the wall. But it somehow appears on the other side of the wall. And we know Not just that it appears on the other side, we know how many are going to appear on the other side of the well. Very, very accurately. How accurately? So that your phone will work. That's how accurately. All of your phones work on this principle that some will get through the wall, and we know exactly how many. So this is just too complex, and it makes us dizzy. So let's just see, can we use this idea? And the answer is yes. We have electric currents and chemical effects. We have televisions and semiconductors. We have superconductors. We have MRI machines. We have scanning tunneling electron microscopes. We use this stuff all the time, and we don't understand it. And then, of course, in 1936, somebody discovered a new kind of electron, and I remember, I think it was Pauli said, Fermi said, wait, a new muon, who, you know, like at a restaurant, it's like, who ordered that? We don't want that. Nobody wants it. We don't like this. We don't need another. We're confused enough. Don't give us another particle. And now we have tauons and leptons and all sorts of things. But we're so accustomed to the electron. We're so accustomed to the electron that the model we have, we feel so good about that we think we understand it. So let's start with the most fundamental part, the part we started with the attraction and repulsion of the tape. And we say, oh yeah, some charges are plus, some are negative. The electron has a negative charge and the proton has a positive charge. And we write that down on our examinations as if we understand it. And so I ask you, and what is this charge? What does it look like? Does the proton have a little plus sign on it? Does the electron have a little minus sign on it? What does charge mean? Is it really a physical property, or is it something we invented to explain these results? And why are there two charges, plus and minus? Why don't we have a universe with 3 charges or 4 charges? Why only 2 distinct kinds? Why can't we have an ABC charge? So in school, we want to ask the questions. In school, we want to ask these 4 essential questions. Well, let me go back. How do we describe it? With a wave function, a mathematical function. That's the electron as we know it. How does it behave? Well, not like anything I know. So the question is, did we invent the electron or did we discover it? So in school, I insist that we assign our students 4 essential questions. What does it mean? How do we know? Why do we believe? And why should I care? The what does it mean, we do a very good job with. The electron has a negative charge. The electron's part of the atom. We're very good at this. What does it mean? We're not as good at the how do we know, but that's the important part. That's the science. Let's do experiments and let's try to interpret those experiments so that they make sense to us. And then we get to the why do we believe in the electron? We never see an electron. Nobody's ever seen an electron. We can describe it as a wave function, but the wave function is never observed. The electron behaves strangely, as the double slit experiment shows, and the tunneling. So I wonder, is the electron real? Is truth real? Is time real? Is coincidence real? We pretend we know about the electron. I don't know what we do about truth, time, and coincidence. Did we invent the electron or discover it? Why do we believe in the electron? It helps us explain experimental observations. It connects charge to light. It predicts the spectra of gases. It has simplicity to it. It is far-ranging. It is part of a larger theory of matter. But the nature of science, it's so unlike anything we've ever seen. Will our model change? Yes, it will. How? I don't know. But here are explanations for the double and slit experiment. What you have is 12 different explanations, from the Copenhagen interpretation to de Broglie-Bohm to the information-based to the many worlds theory. And the bar graph shows you how many physicists believe in each of these. And that's the current state of our knowledge of the electron. So there are a few which nobody believes in. Good. But look at this. Nobody agrees on what is the electron and how does it make sense. So why should we care? Well, we have technologies. We need new technologies and engineers. It's a new way of looking at the world. It's new examples of where our intuition fails us. Was it invented or discovered, the electron? I don't know. Was Michelangelo's statue invented or discovered? Is love invented or discovered? Is the right path, in honor of Gandhiji's 150th anniversary, always choose the right path and speak the truth? Are those inventions or discoveries? The unexamined life is not worth living, Socrates. The electron. David Attenborough said, "It seems to me that the natural world is the greatest source of excitement, the greatest source of visual beauty, the greatest source of intellectual interest. It is the greatest source of so much in life that makes life worth living." And T.S. Eliot, not talking about the electron, but talking about other things, said, "We shall not cease from exploration, and the end of our exploring will be to arrive where we started and know the place for the first time." Thank you.